Hello and welcome back to this lecture number 16. We are studying Hermite polynomials. Let me start sharing these slides and we will continue our study of Hermite polynomials. So, all right, I hope all of you can see these slides now. Yeah, okay. So, Hermite polynomials are the polynomials which are going to give you a very nice approximation for the function because it agrees with the value of the function at given nodes and its derivative agrees with the value of the derivative on these nodes. So this is what the Hermite interpolating polynomial is, and we have also studied how to compute this. In fact, what one has is that there are these hi that one can compute. So they are for I going from 0 to n. So you have h0, h1 up to hn, n plus 1 polynomials hi, and then there are these n plus 1 yet another polynomials which are hi hat. And with these, then you just simply have to, these hi and hi hat, they are solutions to some very special cases of this problem. And so you simply take their sum with with corresponding coefficients to be f of xi and f prime xi. So f of xi are the coefficients for hi and f prime xi are the coefficients for hi hat. So this is what we do. How do you compute hi and hi hat? They are computed in this following way. I have explained in the last lecture the motivation for defining hi and hi hat in this way, and the li are nothing but the Lagrange polynomials for the data xi, f of xi. These are the polynomials that we know quite well until now. So there is an error, of course, for these Hermite polynomials, just like there were errors for Taylor polynomials and also for the Lagrange polynomials. So there is an error for the Hermite polynomials h2n plus 1, and we will see how this error can be written down. So if you have a function which is 2n plus 2 times continuously differentiable, suppose there are these n plus 1 distinct nodes which are given in the interval AB, and for the data xi, fxi and f prime xi, we have the Hermite polynomial h2n plus 1. It will be a polynomial whose degree will be a maximum of 2n plus 1. So we have these data given to us, and then for every x in AB, there is a xi x in the open AB. Okay, so for every x in the interval closed and bounded interval AB, there is some xi x in the open AB with the property that the error, which is fx minus h2n plus 1x, is of this particular form: x minus x naught whole square dot 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 x minus xn whole square divided by 2n plus 2 factorial, the 2n plus 2th derivative of your function evaluated on xi x. So in our last lecture, we had actually taken a very basic data and we computed the Hermite polynomial for that. Let's try to see what the error will turn out to be for that data that we have. So our data, I'm sure you will all remember, is this. You had the function values at 3 nodes which were -1, 1, 0 and 1. They were 2, 1 and 2, and the derivative was -8, 0, 8. So this was our data, and for this data now the nodes are x0 which is -1, x1 which is 0 and x2 which is 1. So since n is 2, we are going to get our polynomial to be a polynomial of degree at most 5. In fact, it turned out that we had the polynomial of degree 4, but we will call it h5 of x, the fifth, the interpolating polynomial for the given data which has 0, 1 and 2. So there are 3 distinct nodes, and so therefore we are going to look at the polynomial h5. And our formula said that you had to take x minus x naught whole square, but x naught is -1. And so you get x plus 1 whole square. The next term will be x square because it is x minus x1 whole square, but x1 is 0. So you get x square, and finally you have x minus x2 whole square, which then becomes x minus 1 whole square. N is 2 here because we have 0, 1, 2. So 2n plus 2, that is 6. So we get 6 factorial, sixth derivative of your function at xi x. So now we need to know what the function was. So I had constructed this data for a function whose degree was slightly more than 6. In fact, the function was x power 8 plus 1. So you can quickly check that the values at minus 1, 0 and 1 are the values that we have here. The derivative of this function is 8 x power 7, and therefore you have that the value of the derivative on 0 is 0, on 1 it is 8, and on minus 1 it is minus 8. So this data was constructed using this function. We have also computed the fifth, the h5, the polynomial, already in the last lecture. We have the numerator of the error term, which is x plus 1 square, x minus 1 whole square. Then you have 6 factorial. What is the sixth derivative of this function? Once you know the function, you can compute the sixth derivative quite easily. It is 2160 into x square. This 2160 is simply 8 into 7 into 6 into 5 into 4 into 3. So that's the number 2160. You can check that. In fact, this is a nice little problem that whenever you take consecutive r integers, which are all positive. So take r consecutive natural numbers from whatever place you start. So you may say you are looking at s plus 1, s plus 2, dot, 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 up to s plus r minus 1. So these are the r consecutive natural numbers. Take the product. This product is always divisible by r factorial. Okay, so we have that this 2160, which is the product of 6 consecutive integers starting from 3. So 3, 4, 5, 6, 7, 8. 6 consecutive integers, and such a product is divisible by 6 factorial, the division being 28. So what we will have, we will have that this sixth derivative at xi x will be 2160 xi x whole square. All right, so we are going to compute the difference fx minus h5x. We will divide by the numerator, which is x plus 1 whole square, x square into x minus 1 whole square. Then we have 28 into xi x whole square. That's what we have. We of course have that the computed Hermite polynomial is 3x power 4 minus 2x square plus 1. So let's compute the difference. X minus h5x. This is simply this particular difference. 1 will get cancelled right away. And after cancelling once, we see that x square is going to divide the difference. So you have the answer to be x square into some polynomial. Now in this polynomial, if you put the value x equal to 1, you see that you get 0. 1 minus 3 plus 2. So that is 0. So x minus 1 divides this polynomial. Moreover, the derivative of this division polynomial, which becomes 6x power 5 minus 6x, the derivative also has 1 as a root. And therefore, x minus 1 square divides this polynomial. Okay, we have already computed what is the multiplicity of some number as a root of the polynomial. So here we see that the multiplicity is at least 2. We have x minus 1 whole square, and then we have some polynomial. Now you check that when you put x equal to minus 1, you get 0, and moreover for the derivative also you get 0. So minus 1 is a root of multiplicity at least 2, which means to say that x plus 1 square divides the polynomial. So this is what we have. So the difference fx minus h5x divided by x square, x minus 1 square, x plus 1 square is x square plus 2. And this is 28 into xi x square. So that gives us that xi x square is x square plus 2 upon 28. And then we have a formula for xi x, which is the square root of x square plus 2 upon 28. So this is something that every mathematics teacher emphasizes, that we cannot write down the form for the error. You cannot write down the form for the error. That's when you are looking at the general case. But when you have a particular polynomial, of course you can write down the error, and this is the way we have done it. Whenever you have a particular polynomial, you can write the error down. Now, one thing we should notice here is that it's a square root, and of course x square is a positive number, and then everything else is positive. So under the square root you have positive numbers. So the square root gives you a real number. We are not getting a non-real complex number, but we have to decide on the sign of this xi x. For continuity reasons, you have to take either the negative sign throughout or take positive sign throughout. We will just take positive sign. Okay. Of course, it doesn't matter what sign you take, because what really matters is xi x whole square. The error is given by xi x whole square. And so the error is indeed x square plus 2 upon 28. That's the error that we have. And one also notices that when you have x from the interval -1 to 1, then x square will go from 0 to 1, and the denominator inside the square root sign, the numerator inside the square root sign is x square plus 2. X square is from 0 to 1, so x square plus 2 goes from 2 to 3. And then you divide it by 28, so you get something between 2 by 28 and 3 by 28. So this is definitely within the interval 0 to 1, and so you also have it within the interval -1, 1, the open interval. Of course, I should also point out that this is the error for our data with the function fx equal to x power 8 plus 1. I told you that when you have a finite data, you may have several polynomials of higher and higher degree representing it. So if your function changes, the fx changes, then there is no doubt that the error form will also change. Okay, so we have studied how to write the Hermite polynomials. We have also studied how to write down the error form for a given data corresponding to a given function. Now, let's see whether we can use our earlier work that we have done using the divided differences to write down the Hermite polynomials h2n plus 1. So this is something which is a very nice application of definition of divided differences as a function. We have actually looked at divided differences not just as some numbers, but it's a function that we can define on the whole real line. And this is what is going to come handy for us. We will use it and write our Hermite polynomial using the divided differences table. So whenever you have these n plus 1 distinct nodes and the values of the function and its derivative at these numbers be given, what we do is that from these distinct nodes, we construct one more sequence where the nodes may not be distinct. So we define a new sequence. Now, of course, a sequence doesn't, sequence can be infinite, but here by sequence, we mean it in a very broad sense. You may call it a set if you really wish. I'm calling it a sequence because we are putting it in some order. That's the only thing. So we have Z0, Z1 up to Z2n. We started with X0, X1 up to Xn, and we are getting double the number of nodes, and there will be repetitions, and you may perhaps already see these repetitions. What happens is that we start with X0, X0, X1, X1, X2, X2, and so on. So our Zi and Z2i plus 1 will be the same, and they will be equal to Xi for each I going from 0 to n. So these nodes, which are no more distinct now, they will read Z0 equal to X0, Z1 equal to X0, Z2 equal to X1, Z3 equal to X1, dot, 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 Z2n minus 1 equal to Z2n equal to Xn. So this is okay. So I see that there is a small mistake here. The new sequence by this construction has 2n plus 1 nodes. It should be 2n. So the last one should be 2n minus 1. I'll make this change when I write it down in the. No, it should be 2n plus 1, because we should get here we had n plus 1 and there we should get 2n plus 2. So I'll make that change. Okay, so this is the new sequence that we have defined, and for this sequence we will construct our table of divided differences. But we have to be careful because whenever we have xi, xi and fxi, fxi, the next divided difference will be the derivative. So the divided difference of z2i, z2i plus 1, which is the divided difference of xi comma xi, that will have to be f prime xi. This is our definition of the divided difference, as when there are repetitions of the values. So then we have our formula for computing the Hermite polynomials, and it's the similar formula that we have for the Lagrange polynomials, the interpolating polynomials, which is simply that you start with f of z naught, and then you have z naught up to zk, x minus z naught up to x minus z k minus 1. So if you are looking at forward differences, so you would be looking at the top slanted set of numbers, and you will start with the top one, which is f of z naught. To that you are not multiplying by any polynomial. Then you go to the next one, which is the derivative at x naught, and to that you will multiply by x minus x naught. So this for k equal to 1 will be f of z naught z1, which is f prime x1, and you would have multiplied to that by x minus z naught, which is x minus x naught. Then you would have f of z naught z1 z2, and to that you will multiply by f of x minus z naught into x minus z1. So that's the way you would start doing this whole computation. Let's do it for the data that we already had. But before doing that, let me just explain this to you, that this is how the table will look like. We have the leftmost column, which is the column of the values of the nodes, which are no more distinct now. Then you have the function values, which are also no more distinct. And then we take the first divided differences. So we see here that f of z naught z1 is indeed f prime at x naught. Then f of z1 z2, this can be computed. It is simply f of z2 minus f z1 upon z2 minus z1. Then you have f z2 z3, which is the derivative at x1, and so on. And finally, this is the way we are going to compute the divided differences. So our data, if you remember, was this: x naught is minus 1, f of x naught is 2, f prime x naught is minus 8, x1 is 0, f of x1 is 1, f prime x1 is 0, x2 is 1, f of x2 is 2, and f prime at x2 is 8. We are going to construct our divided differences data. Here we write down the nodes. We see that they are not distinct, and these are the function values. So for minus 1, the function value is indeed 2. For 0, the function value is 1. And for 1, the function value is 2. Now we have to go to the next level to compute the divided differences, and this is how we compute them. Notice here that this is the derivative. The numbers in blue are the derivatives, and the remaining numbers, so this minus 1, for instance, is computed by looking at 1 minus 2, which is minus 1, and we are going to divide to that by 0 minus minus 1, so that is just 1. So we therefore get this to be minus 1, this is 1. So this is the way we have computed the first divided differences. The second divided differences would be minus 1 minus minus 8. So minus 1 plus 8, that is 7, and 0 minus minus 1, so that is just 1. So we get it to be 7, and similarly 0 minus minus 1, that is 1. Denominator is 1. This 1 minus 0 is 1, the denominator is 1. 8 minus 1 is 7, and the denominator is 1. So these are the second divided differences. These are the third divided differences. These are the fourth divided differences, and these are the fifth divided differences. Since we have a data consisting of 6 numbers, 6 nodes, we will go up to the fifth divided differences, because you would have 6 entries in the first column, then 5, then 4, 3, 2, and 1. And we are starting with the 0th divided differences. The 6th one corresponds to the function values, which are the 0th divided differences. Then the first, second, third, fourth, fifth. this is how we have. Now we could use any method from this to write down our interpolating polynomial, but we are going to use the forward differences. So we are going to use these numbers in the color magenta to write down our Hermite polynomial. And so the Hermite polynomial is then just the f of z naught value, which is 2, plus the next value multiplied by x minus z naught, which is minus 1. So you have minus 8 into x plus 1, because x minus minus 1 is x plus 1. Next would be 7 into, now z0 and z1 are both minus 1. So we will be multiplying to 7 by x plus 1 square. Next is minus 6. But to minus 6, we will have to multiply by 3 linear polynomials. X minus 0, x plus 1 square. So it is indeed minus 6 into x plus 1 whole square into x. And then we will multiply to the next number, which is 3, by x plus 1 whole square x square. And the final divided difference is 0, so we don't have to write it down. Okay, so from here we see immediately that the degree of this h5 is not 5. The fifth divided difference is in fact 0. So that term has vanished. And all the terms except the last term have degree less than 4. So the degree 4 contribution comes only from this highlighted term, and indeed we see that the Hermite polynomial here h5x is 3x power 4 minus 2x square plus 1. So this computation can easily be checked. The x cube terms, x terms cancel out in this computation, and the x power 4, x square, and the constant terms are indeed the ones as given. So this is the way, just for fun, you may want to compute this by any way. For instance, you may start from here at 1, then go to minus 1, then go to 7, then go to minus 6, minus 3, and 0. You may compute this, multiply to these numbers by suitable linear factors, and do check whether it gives you the correct Hermite polynomial. Okay, so once we have done this, there is something that we have to note. So we are, until now, we are concerned with the approximation of arbitrary functions on closed intervals using a single polynomial. What we are doing is that we are finally approximating our function, because we are looking at some data of the function values. We find a polynomial which fits those function values and hope that this polynomial will approximate our function in a nice way. Okay, so sometime we also demand that the derivative values be the same and so on. But even then, what happens is that when you are looking at a single polynomial to approximate this whole data, if the data is really large, then your polynomial is likely to have a higher degree, and these polynomials are not good, because higher degrees polynomials can oscillate erratically. So what it means to say is that whenever you have a small change in your function values, there are high degree coefficients, there are high degree terms in the polynomial. Therefore, the value of the polynomial can change in a big way. There might be large fluctuations over the entire range. This is what happens when you have a high degree polynomial, which is interpolating your given function, which we are trying to use to approximate the given function. So let's see an example. It's a very interesting example that we are going to see now. And what we have is that we have this picture of the flying duck, and we are trying to look at the top profile of this duck. We will choose points on the curve, which is the top profile of this flying duck, and we want to approximate this top profile. So we choose the points, we look at the function, and look at the interpolating polynomials. So we put the flying duck in a grid and compute the values. So observe that whenever the curve is changing rapidly, then we have more polynomials. So this is something that you may look at here. For instance, between 4 and 5, there is one value just before 4 which looks like 3.9, and then you have two values, and then you have a value at 5. in comparison with the values after 5, the nodes after 5, there is some kind of a regular behavior. So after 5 we have just 6, then 7, then 8, and then we have gone ahead than 9, maybe 9.2, and then after 10 we may actually have gone to 10.5, and then once again we have to take more nodes because the change in the curve is more rapid than the earlier changes. So this is what we have done to approximate the top profile in a better way. And the nodes, if you count the number of nodes here, there are total 21 nodes. So we will write down the nodes and the corresponding function values. Here we have started with the first seven nodes. We go from 0.9, then 1.3, 1.9, 2.1, 2.63, and 3.9. The values are going to be, after all, bounded. The values will not go high because it's some kind of a horizontal graph of the curve that we see. These are the next 7 entries. So after 3.9 we have 4.4, 4.7. So between 3 and 4 we do not have those many values, but from 4 to 5 we have already 4.4, 4.7, and 5. And then I already remarked that after 5 we have 6, 7, 8, 9.2, and then 10.5. And then again between 10.5 and 12 we have three values, 11.3, 11.6. So from 10.5 we have gone already to 11.3, but then we have 11.6 and 12, then 12.6, 13, and 13.3. These are the 21 nodes, and there are these corresponding values. So here the polynomial will be of degree less than or equal to 20. It does happen to be a polynomial of degree 20. Don't ask me what this polynomial is. It will take quite a lot of space to write this polynomial down. But what we are going to do is that we will superimpose the graph of this degree 20 polynomial on the back of our flying duck and see how the approximation looks like. And here we see that the blue line gives you the graph of the function, and it's a very erratic, a very strange behavior, very strange illustration for the back of our duck. Doesn't matter whether the duck is flying or sitting. The graph doesn't look like the back of a duck. So this is the kind of errors that we have when we have higher degree polynomials. In comparison, if you had just taken linear interpolating polynomial for each successive pair of points, that would have given us a much better approximation. So the idea is that we will use linear interpolation, or maybe degree 2 or degree 3. We will not go beyond degree 3, but we will use piecewise linear polynomial interpolation. And what we will try to do is that whenever we are using the piecewise polynomial interpolation, we will try to match them. We will try to pest them in a nice way, so that when you pest them, even at that point you are not losing too much data. For instance, if you were just going to use the linear interpolation, then there would be nodes, because there will be some sharp edges, there will be some sharp points. When you have something like, wherever the graph changes rapidly, say for 4.4 to 4.7 and 4.7 to 5, you would have something which looks like a small v, or maybe slightly elongated, slightly disfigured v, but then there is a tip of the v which will give you problem when you are trying to compute the derivative of the function that you are obtaining by doing this piecewise polynomial interpolation. So those are the things that we are going to do from next time on, that we are going to look at piecewise polynomial interpolation. So hang on with this course. The course is going to be more and more interesting, and I hope to see you in our next lecture. Thank you.